Hello and welcome to my online video tutorial on the subject mathematics. Today the topic of discussion will be differential equations. Myself Aman Jaiswal, a third year mechanical engineering student of Indian School of Mines Dhanbad. So let's start with our topic of discussion, differential equations. What exactly are differential equations? Differential equations are a simple relation which it gives between a dependent as well as an independent variable with its derivative of any order are called differential equations. So when we proceed with the differential equations, we either solve a differential equation or we form a differential equation from a general equation. So when we form a general equation, we integrate the number of times the derivative we have or the order of derivative we have, which we are going to learn in this tutorial. And the making a differential equation is differentiating the number of times the constants we have. So we differentiate according to the number of arbitrary constants we have in the differential equation. So these are some different types of differential equations which we are going to study. The one is simple equation, and its equation is given as well as the solution of it is given. That is, we integrate and we just find the answer. Then we have a variable separable. It is a very interesting one. We just separate the variables and then we integrate to find the result. Then we have reducible to variable separable. We make some assumption like ax plus by plus c equals to z to make it a variable separable. Then we have homogeneous equations. This is the type of homogeneous equation we have over here, and then we make some substitution to solve for the particular substitution. Then we substitute it back to get our general equation. We'll go in detail in the following tutorial. Then we have linear equation, in which we find the integrating factor, and then there is a simple equation we solve to get our general equation. So let's proceed. What are the order and degree of a differential equation? To continue with that, then consider a differential equation like this: d2y by dx square to the power whole square plus x dy by dx plus x square equal to 0. Now we see that the order is 2 and the degree of 2 of this equation. Why? The order is the highest derivative present in any equation, and in this equation it is 2. So the order is simply 2. Therefore, whenever someone asks you what is the order of a given equation, you just see the highest derivative present in that equation. Okay, now the degree. What is the degree? The degree is the highest power of that derivative we have. Then we call it as a degree. Here the degree is 2. Now we have some points to remember when solving the differential equation of nth degree. For evaluating the unknown functions, we have to integrate equation n times, and therefore in the result we shall get the n number of constants. Then we just combine all the constants and give it a simple c or c1 or whatever notation you want to give. So now let's do an example to generate a differential equation from a given equation. Consider this equation: y equals to x square plus c1 e to the power 2x plus c2 e to the power 3x. Okay, here c1 and c2 are the arbitrary constants, and from different values of c1 and c2 we will get different curves, and from this equation they all will be satisfying that differential equation we are about to find. That is a kind of tricky, so you can read whatever I have written over here by just simply pausing it, and you can understand what it is, and in the detail we'll also find the concept of it is. So let's proceed. We have to differentiate the exact number of times as we have constant, and therefore we do it 2 times because there are c1 and c2. So the first derivative y dash, or we call it as dy by dx. We find the first derivative as 2x plus c1 e to the power 2x into 2 plus c2 e to the power 3x into 3. This is our first derivative equation. Now we find the second derivative y double dash, or we can say it as d2y by dx square equals to 2 plus 4 c1 e to the power 2x plus 9 c3 e to the power 3x. These are the simple differentiations we have done by the simple chain rule. Now by equating all the 3 equations, we can eliminate C1 and C2. These are our arbitrary constants by simple elimination method we have studied in class 10th. So after solving it, we'll obtain this equation and we can simplify it to get our desired answer. That is our desired answer. So that is how we proceed to find a differential equation in simple form. Now some tools to solve it. Always count the number of arbitrary constants. Whenever we are proceeding with an equation or a differential equation to get our desired result, we should initially count the number of arbitrary constants we have. Then we have to differentiate the exact number of times as the constants are present. Okay, when we are finding a differential equation, we have to differentiate the exact number of times as the constants are present so that we can find the exact number of equations which are sufficient enough to eliminate the constants. Then we eliminate the constant by simple elimination method, or we can do it by substitution method, and then we simplify to get the desired result. Now we shall discuss the different types of differential equations and how to solve them. The first one is variable separable. As the name suggests, variable separable method, in that we separate the variables and then we simply integrate it to get our desired general equation. Okay, so mathematically the differential equation, or we call it as DE, has a form dy by dx equals to f of x divided by g of y. F of x is the function of x only and g of y is the function of y only. Then we solve the following differential equation just by integrating and just by rearranging the variables to get our desired result. Here c is the arbitrary constant and we have to put it every time when we integrate. Okay, so to understand this concept more properly, let's find the general equation of the following DE, that is x square dx plus y dy equals to 0. By looking at this equation, it can be observed that variables can be separated. Therefore, it is a separable form of DE. Now, we just proceed with the equation integrating x square dx plus integration y dy equals to 0. Then we get the result x cube divided by 3 plus y square divided by 2 equals to c, and c is the arbitrary constant. We have to put it every time, as I have already told you, after the integration. So this is the desired result. It is a simpler one, so let's solve some complex examples to make it more clear. So we have to solve this given differential equation, that is xy square dy by dx equals to 1 minus x square plus y square minus x square y square. Okay, so this is a kind of tricky one, so we have to make some arrangements in order to make it in the form of variable separable. So we have to first adjust the variables x y square dy by dx, then we take minus of x square common from minus x square minus x square y square. Then we can solve it the equation like that, 1 minus x square 1 plus y square. Then we separate the variables by rearranging. We can get this result very easily. Okay, so we add and subtract 1 in the numerator of the left hand side to make it suitable for the integration. Then we get the desired equation so that we can integrate it easily. Now this equation has been reduced to variable separable form. Now another step is to integrate to get a general equation, which is very simple process, just by integrating 1 by y square plus 1 by x and x. So we can get our desired result like that. So now we have some other example. Y minus x dy by dx is equals to lambda y square plus dy by dx. Now we can see that this is also a form of variable separable, but we have to make some few adjustments. So first of all, we have to make it a variable separable form. Now what we are going to do for that, we just multiply lambda in the bracket, so we get this right hand side as lambda y square plus lambda dy by dx. Okay, so we shift our lambda dy by dx to the left hand side so that we can get this particular equation we have right now. So after taking it, we just take dy by dx common and simplify to get this equation y minus lambda y square is equals to dy by dx x plus lambda. Now we arrange dy and dx on the both sides as well as their variables to get our desired equation, which is this, and it can be easily integrated to get our desired result. So integrating, we'll get ln y, that is log y to the base e. We have to particularly understand that when we get log y and when we get ln y, when there is log y, it is by default is log y is base 10, and when we use ln y, it is by default base e. So we get our result ln y minus ln 1 minus lambda y is equals to ln x plus lambda y plus c. So we can rearrange it and we get our desired answer like that. Ln y upon 1 minus lambda y is equals to ln x plus lambda plus ln c2. Now some important tools to solve variable separable equations. First of all, we have to check if the variable can be separated or not. Then we can proceed with our variable separable method. And then we try to take dy by dx on one side and rest of the variables on the other. So when we are proceeding in a right path, we'll observe that all the y variables will come on numerator or the denominator and vice versa for x variable. So that is how we solve, and that is how we conclude that it is a variable separable form. Then it is just basic integration after simplifying the equation as much as possible to make the integration very simple. That is very important in order to solve a differential equation by integration. We have homogeneous equations. One of the most important form of equations. We can determine any equation as homogeneous equation when it satisfies the given relation, that is f of lambda x comma lambda y, that is function of lambda x as well as lambda y. It should be equals to lambda to the power n f of x comma y. Now what is that? We'll prove what the relation is and how to solve it, that homogeneous equation. So if this particular condition is satisfied, we are allowed to proceed by solving the problem by homogeneous equation method. So to make this concept more clear, let's solve a different example. So we have two equations and we have to satisfy that condition so that we can tell it is a homogeneous equations. F of xy is equals to x cube plus y cube, as well as f of xy equals to x square plus xy plus y square. Now how we prove it as these are homogeneous equations? Step 1. Determine the homogeneity of these given equations. To prove these equations as homogeneous, we have to substitute as follows. X equals to lambda x, y is equals to lambda y for both the equations. Now as I have already told you, we have to make the function like f of lambda x comma lambda y. So when we substitute x as lambda x, y as lambda y, we'll get this equation as f of lambda x and this equation f of lambda x comma lambda y for both the equations. So now let's proceed with our given substitution. We'll get like that. F of lambda x comma lambda y is equals to lambda x cube plus lambda y cube. We have to just substitute the values of x with values of lambda x and the values of y with values of lambda y. So we will get f of lambda x comma lambda y is equals to lambda cube x cube plus lambda cube y cube. So we get, by taking lambda cube common, lambda cube x cube plus y cube, and that comes up to lambda cube f of xy. This is our old equation. So from this relation we can say that f of lambda x comma lambda y is equals to lambda to the power n f of xy. So this is a homogeneous equation because it satisfies the only condition we have for the homogeneity. Simply for the equation 2 we can solve it like that. You can just check it out, and it also gives the same condition which is satisfied over here. So that's how we can say that these both are homogeneous equations. Then we have to provide some necessity substitution in order to proceed. Now we are proceeding for our homogeneous method. The basic substitution we have is y is equals to vx. The equation contains dy by dx. So by differentiating this substituting equation, that is dy by dx is equals to v plus x dv by dx. That has come with our basic chain rule we have studied in class 11th. So we put x equals to vy when equation have dx by dy. Then we substitute by differentiating dx equals to dy is equals to v plus dv by dx. Now we have to keep this in mind. Whenever we have dy by dx, we have to put y is equals to vx. When we have dx equals to dy, we put x equals to vy. Now we equate the values of dy by dx to get the necessary results. In both the equations, we get the values of dy by dx as f of xy. So we equate dy by dx is equals to f of xy. We compute both the values of dy by dx to get the desired result. One which we have from the given equation, and the second one which we get by the equation y is equals to vx, and then differentiating with respect to x to get the value of dy by dx. We can solve more examples on this homogeneity after this shortcut method, which is very important to solve very quickly in the competitive exams. So what is the trick to solve very quickly? When we put the substitution y is equals to vx or x equals to vy according to the convenience or the nature equations, instead of putting the values of y and x separately in the given equation in terms of v, we try to minimize the labor by putting y is equals to v and x equals to 1. I will tell you later on how it is very beneficial to solve the equations very simpler manner. So let us prove it, and we shall compare this shortcut method with our traditional one. So we have our differential equation dy by dx is equals to 2x minus y upon x plus y. Now we have shortcut method on left hand side and traditional method on the right hand side. So first we have to prove it that our shortcut method is authentic and it can be operated on any homogeneous equation we have. So in the shortcut method we put y is equals to v and x equals to 1. So by putting the same, we'll get dy by dx as is equals to 2 minus v upon 1 plus v. Now in the traditional method we have y equals to vx and x equals to simply x. So we get like that, dy by dx equals to 2x minus vx upon x plus vx, and dy by dx is equals to x into 2 minus v upon x 1 plus v. So by simplifying, we get on the both equations 2 minus v upon 1 plus v, and the another one 2 minus v upon 1 plus v. So this proves that our shortcut method is very much authentic and we can use it in any number of homogeneous equations. It comes very handy when we are dealing with very much complicated equations. So further solving it, we put y is equals to vx to get the value of dy by dx. Now interestingly, there is a trick in it. You have done y is equals to v and x equals to 1 to get the value of dy by dx in the given equation. Now to get another value of dy by dx, we cannot put y is equals to v and x equals to 1. We have to just go on with y is equals to vx. Okay, continuing with that, dy by dx is equals to v plus x dv by dx. Now equating both the equations, the equation we have from our question as well as the equation we have just got, that sums up to v plus x dv by dx is equals to 2 minus v 1 plus v. That implies x dv by dx is equals to 2 minus v upon 1 plus v minus v. We just took this particular v on the right hand side to get this. Now further solving it, we'll get x dv by dx, and taking the LCM of minus v, we'll get this equation. By further solving it, we get this x dv by dx 3 minus 1 plus v square upon 1 plus v. How we did that? We just made it a perfect square. We used to do it in class 10th. So it comes up to x dv by dx 3 minus z square upon z. Now what is z? We have to put 1 plus v is equals to z, so that if we differentiate this particular equation with respect to x, we get dv by dx is equals to dz by dx. So there is no problem in substituting dv by dx equals to dz by dx, as well as 1 plus v is equals to z. So we just did it to make the integration more simpler so that we can solve it easily. Now we get this equation like that: x dz by dx is equals to 3 minus z square upon z. Now we have to take care of this. When we are dealing with z and x, the differentiated variable should be z, not y or not v, because we have substituted from v to z. Now this equation is given as dx by x is equals to z dz upon 3 minus z square. It has been just done by rearranging the variables. Now it is simply a equation which can be solved very easily by integration. So now next step is integrating on both the sides. We'll get this: z dz upon 3 minus z square is equals to dx by x plus c. Now we have to completely focus on the arbitrary constants we are using, because we are using all the different constants in every equation. Interestingly, we have given different notations on every equation of constants we have right now. So we'll discuss it later, what is the relevance of giving different notations after doing every single operation in the given equations. So let's do the integration. We get z dz upon 3 minus z square is equals to integration of dx plus c. We differentiate by the following way and we get minus half ln 3 minus z square in the mod, which is always greater than 0, the mod, and equals to ln x plus ln c1. ln c1 is the integration of log c, or we can say that we have given the notation ln just because to balance the equation, because all the variables are in the log. So by continuing this, we'll get these different equations and we solve it further to get our desired equations like that: x square equals to 2 minus v square minus 2v is equals to c3. Now what we have done here, we have just integrated and we have just cancelled the log on the both sides to get our general equation. After getting this equation, we substitute back the value of v in terms of y to get our general equation. Now how we do that? We put simply v equals to yx. We get this equation, that is x square into 2 minus y upon x square minus 2y by x is equals to c3. That is equals to x square 2 minus y square by x square minus 2y by x equals to c3. That is simply opening the bracket. So we get our desired answer as 2x square minus y square minus 2x square is equals to c3. This is our desired answer. So an important thing to remember is the arbitrary constant we put, as we have just discussed earlier. As you can see, we have used different constant notations such as c1, c2, c3 and c. It is very important to observe their actual relevance in order to get the concept properly, which is explained as follows. In equation 3, constant c is used after the integration. In equation 4, constant c1 is used to make it into logarithm function so that it can be equated with the rest of the equation, as all the variables are the mean of log. The mean is the number we use in the log. This is called the mean. In equation 5, constant c2 is used because the negative sign of different side of the equation is taken on the side of the constant, here changing the value of the constant notation. In equation 6, constant c3 is used to sum up all the constant values our desired equation will possess. It is very important to observe and to give the good notation because it is very important in the 12th board examinations as well as in the competitive examinations, in which you cannot just go like that and put any constant you want, because in the definite integrals you particularly need to mention which constant you have got after the integration. So now another equation we have is equation reducible to homogeneous equation. What are these equations? These are some equations which are not actually homogeneous, but after making some adjustments and some substitutions, we can reduce them to the homogeneous equations. So mathematically we can say that dy by dx is equals to f of ax plus by plus c upon dx plus ey plus f. Now clearly ax plus by upon dx plus ey, it is an homogeneous equation, but there are some constants in the equation, that is c and f, which are preventing us to make it a homogeneous equation. So how we eliminate them? We have to make some necessary substitutions in order to make it in a homogeneous form and to eliminate the constants c and f from the equation. And how we do that? We have to put small x is equals to capital X plus h and small y is equals to capital Y plus k, as you can see over here. So how can we examine, or how can you get the value of h and k? H and k should be taken such that it should satisfy these necessary conditions, which are ah plus bk plus c is equals to 0 and dh plus ek plus f is equals to 0. These are the necessary or the must conditions h and k should satisfy in order to make our given equation a homogeneous equation. Now putting the values of x and y, or we can say that capital X and Y, in order to get our equation as a homogeneous equation. So now putting it, we can get it as f of ax plus by plus ah plus bk plus c upon dx plus ey plus dh plus ek plus f. Now we can say that ah plus bk plus c and dh plus ek plus f should be equals to 0 because it is satisfying the necessary condition. After putting both of them equals to 0, we can get it as dy by dx is equals to f of ax plus by upon dx plus ey. This is simply a homogeneous equation we have just solved in our previous topic. Now it is converted into the homogeneous equation. So we should solve some examples in order to make it a bit more clear. Now we have this equation dy by dx equals to 2y minus x minus 4 upon y minus 3x plus 3. Now this is a simply equation which can be reduced to the homogeneous equation. So we have to do some substitution as well as determine the values of h and k so that we can put these necessary conditions and we can make it a homogeneous equation. So now doing the substitution, that is small x equals to x plus h comma y is equals to y plus k and 2h minus k minus 4 equals to 0, h minus 3k plus 3 equals to 0. Now a, b, c, d, e and f are all from this equation, that is a, 2 is equals to a, minus 1 is equals to b, c is equals to minus 4, as well as we can find e, d, f also. So solving, we get h equals to 2 and k equals to 3 by simply eliminating these two equations. So substitute the values of x and y in the given DE. We'll get dy by dx equals to 2y minus x upon y minus 3x. That is a simple homogeneous equation. Now we're doing our shortcut method, which we have just discussed earlier. Y is equals to v and x equals to 1 to get the value of dy by dx. That is 2v minus 1 upon v minus 3. We make it as an equation number 1. Now going to our previous substitution, that is y equals to vx, we get the value of another dy by dx, that is v plus x dv by dx. Remember that whenever you are doing this substitution, you will always get the second value of dy by dx as this v plus x dv by dx. It is important to remember that you should not always do the differentiation of y and vx to get this value. It is a very general value and it will always come when you put this. So moving further, we equate both these equations 1 and 2. We get this 2v minus 1 upon v minus 3 is equals to v plus x dv by dx. Now solving, we get minus dx upon x is equals to v minus 3 v square minus 5v plus 1. I am not solving it for you. You can do it at your home. It is very easy. It's not so difficult. You should try it by yourself. So this is the equation we are trying to carry out. Now by simple integration, we can, and then we have to substitute it back. Obviously, v equals to y by x with another substitution by putting capital X equals to x minus 2 and capital Y equals to y minus 3. We get our general equation. So this is how we solve the equations which are reducible to homogeneous equation. Now there is a concept, or there is a catch which we have to find out, which is what happens if we are trying to find the values of h and k, but the system of equations or the system of lines doesn't give a solution. And when is that happens? It happens when a upon b is equals to d upon e. When we put this in the equation we have just solved, you cannot find a particular equation. because all h and k will get cancelled. So in this type of equations, or in this type of questions, when you have to make another assumption which can be proved useful in solving these kind of equations. So let's find out what it is. We have to make an assumption as a upon b equals to d upon e equals to lambda, such that we get this a equals to lambda d and b equals to lambda e. So we put this in these substitutions, we'll get ax plus by plus c upon dx plus ey plus f is equals to lambda dx plus ey plus c upon dx plus ey plus f. We have just substituted the value of a as lambda d and value of b as lambda e, and we have taken lambda as common. So this is how we substitute, and then the next substitution will be dx plus ey is equals to v. So therefore, after doing these substitutions, we have to differentiate this equation to get d plus e dy by dx equals to dv by dx, which gives dy by dx equals to 1 upon e dv by dx minus d. What we have done here, we have just taken dy by dx on a separate side and all the variables on the other side. Therefore, it becomes 1 upon e dv by dx minus d is equals to lambda v plus c upon v plus f, which gives dv by dx equals to lambda ev plus ec upon v plus f plus d. Now it is important to observe that how we got the value of dy by dx. We have just put v instead of this and here also, and we have just substitute the value over here. So we get lambda e plus d into v plus ec plus df upon v plus s by simply taking the LCM, and we can simplify this equation like that. Moving further, this is a reduced equation which can be easily converted into the general equation by the method of homogeneous equation. So this is what we do when we have to put some tricks in the particular equations. So we'll solve some more problems like that in our miscellaneous problem section. So we have now our tools to solve. The first one is always see the degree of each variable or set of variables that will be same everywhere in the equation. Like we have seen it before, f of ax plus y upon bx plus y. So in this x and y in the numerator as well as x and y in the denominator, the degree are both the same. Okay, so putting y equals to v and x equals to 1 only applies to the substitution in the given equation, and not when we equate with the derivative of y equals to vx. Exactly, that is what I have told you before. We have to just put y equals to v and x equals to 1 only in the given equation. I am repeating it again and again because it's a common mistake everyone do when performing our shortcut method. Remember to change the notation of arbitrary constant every time operation is done. On the other hand, when we integrate somewhere, or we put a negative sign somewhere, or we put a logarithm function somewhere, we have to change it from c to c1 or c to c3 and vice versa. So this is how we change the notations of constants, and it is very important to do that. Values of h and k should be properly calculated and should satisfy the necessary condition which I have discussed before. It is very important that values of h and k should satisfy both the equations we have. So in the next tutorial we shall discuss another type of differential equation, that is linear equations and miscellaneous problems on all the forms of equations. So thank you so much for watching this video, and stay tuned for the next tutorial where we'll be focusing upon linear equations and other miscellaneous examples. Thanks a lot.